So I came across this interesting visual the other day, which denotes speed of programming languages for running a billion nested loops, right? And there's some work done in all of these billion iterations. And as you can see, C and Rust are the fastest among the whole batch, right? And Python, obviously, like some of you might have already guessed it, is the slowest among them. And the difference is staggering. You see half a second for C and 75 seconds, almost 75 seconds for Python. That means the difference here is close to 150 times, right? C is 150 times faster than Python in this specific case. And the program is simple. So in this video, I want to tell you a little bit about why this is happening, explore a little bit of computer science with you in general, and talk beyond programming languages also. So before we get into the actual explanation of why things are happening, I'll leave the link of this repo below as well, which is the actual source code of this whole, not exactly of this web application, but the results we saw over here. And if you look at the code over here, and if I go to JavaScript and take a look at code.js, you see it's a relatively simple code, right? You just get the number of iterations from command line, then not iterations, this is just a random number basically. Then you get a random number from, the language runtime itself. Then you run an outer loop of 10,000, the inner loop of 100,000, make a simple sum, and you just add a random value to each the element in an array. And then you print out single element from array. And the reason this is done is so that programming languages like C and C++ and Rust maybe, they just don't optimize away the whole loop, right? Because what these compilers can do is that because they are running in O3, for example, third level optimization, they are really smart, right? These are like compiled languages. So compilers have all the information about the types and everything. But over here, because you can see, let me just open the C example. That would be better. In this case, you can see that because you are getting some information from outside world, your compiler just can't optimize away the full loop because it doesn't know what this U is at the, at the compile time. It has to keep this loop because it doesn't know what the result would be. So it would not optimize away the full loop, right? So this is the reason the behavior of this benchmark is the way it is. But let's talk about what's going on over here. You can see like this is extremely slow. Like this is like laughably so slow over here. However, this one is extremely fast, and even JavaScript is doing well in this specific case. So what's happening over here? Let's take a look. Well, very fundamentally speaking, I won't get into very depth of computer science and in general, like what things are working on, what's happening over here. But generally speaking, you know that if you're writing anything like script.c, script.js, script.py, whatever it is, at the end of the day, in order to make sense of what you have written, it has to be executed on a hardware, right? Which is your CPU or GPU, but let's just keep it CPU in this specific video. And CPU doesn't understand for I equal to 0, I less than 10, I plus plus. It doesn't understand that. It understands opcode, right? So it understands you passing things like this. And then every single one of these opcodes is a certain instruction for that CPU in its architecture, right? For example, one of the intermediary representations that we use is assembly, right? Your code, first of all, gets into assembly, which is still human readable, right? So your assembly code is still human readable. You have statements like move, you have statements, I don't remember exactly, but there are statements like add and subtract also, I believe. But there are a bunch of statements in assembly which allow you to see what the exact opcode is going to be, because it's like one step before you start running your code on the CPU exactly, right? So everything at the end of the day has to convert it into assembly, and then it has to go to opcode. Then you might ask that if every language is basically doing the same loop, you can see JavaScript is the same. And if you look at C also, it's pretty much more or less the same loop, right? You just get a random integer from CLI, you calculate a random integer within the runtime, you create an array, you run the loop, and you print the result, right? If you look at Python also, you would see that it's still the same, right? You get a random array from runtime, create a random array, run a loop, print the number. Then why? Why is this taking so much time? Why is this 150 times slower than this one? Well, every language has its own explanation in a way, but let me give you some generic ideas, some things to ponder on if you haven't thought about this. Let's start with what's happening with C. So if we take a look at C as a very simple example, for example, you have int a equal to 5 over here, right? But you know that in C, if you have used C, if you have not used C, let me just tell you, but if you have used C and if you do something like this, int b, for example, and if you try to print b, it's possible that it just gives you a random garbage value, right? However, if I have something like this, let's say if I go over here and if I open console and if I clear this and if I have, let's say var b in JavaScript or maybe let C, something like this. And if I enter C, you can see it specifically gives me undefined, right? Why? The reason C doesn't give you that and the reason JavaScript does give you that. In fact, we can just try it out also. So if I go ahead and open a C playground over here, what you can see over here, if I, let's say if I add int a and then I printf a like this, right? And if I run gcc main.c and then I run a.out over here, you can see it gave me 0 and something over here. So let me just remove the new line also. So for some reason, all of them are 0 for now, but just to let you know, this could be any values, right? So the behavior here is not predictable. So this is one of the things, let's say the variable initialization is one of the things which C does not enforce. The other thing is that if you have something like a pointer over here, right, which can point to something else in the memory, C over here would not stop you from doing that even beyond the scope of what you are allowed to access, right? What that basically means, just to put it simply, is that your code over here is supposed to go to assembly first, yes, but it doesn't just directly go on CPU directly, right? It has to go through the operating system first, right? So over here, you have another layer of integrity which is maintained, which is the operating system. So your operating system is the one that always talks to CPU, not your code. This is one of the things which we usually miss out, that, hey, your code is compiled and then, you know, it's just supposed to run directly on the CPU. That's not what happens. Your operating system takes the charge first, and it is responsible that you don't mess around with things which you don't control as a program, right? C, what it would do is that it would just do whatever you ask it to do without any guardrails in place. So it can technically just, you know, access memories which it's supposed to not access, and your operating system in that case kicks in and just crashes the program. So it maintains the integrity so that, you know, you are just not able to mess around with other processes on the system. What it means is that C by default does not has those guarantees built in, does not has those guardrails built in, not guarantees. So what these guardrails are is exactly what I showed you over here, right? So when I'm initializing a variable, it starts with undefined, not a garbage value. So however small time it may be, but your runtime or JavaScript in this case is spending time to make sure that you are getting a predictable behavior here in this specific case. Similarly, let's say if we take a look at, you know, let me just go back to the JavaScript example, and if I copy this one line, right, and if I paste this over here, and if I try to access some random element, right, over here you can see if I access this A, all of them are 0, right? So that's one thing. All of them are initialized by 0. Something C can do, but it would not be doing that if you wanted to, if you don't want it to. Similarly, if I'm accessing something like this, it knows that it has to return undefined. If you try to do this in Java, it would know that I have to throw an exception, that you are trying to access an element which is outside the bounds of the array. C does not do that. So it does not has those guardrails, but your runtimes do. And small things like these, what they do is they go inside the assembly code, right? Because at the end of the day, when you are accessing an array and if you're incrementing that element, that's not what exactly your runtime is doing, right? It's providing you with certain safeguards that JavaScript on runtime would not throw an error if you're trying to access an element which does not exist, right? So those runtime guarantees also exist in the assembly code, right? So even if you see this code like this, it's not exactly the code equivalent to what you see in Rust, for example. That's the difference. That's where this O3 compiling and all of this stuff kicks in, where the assembly code generated over here, or rather I should say the opcode generated finally, which goes into the CPU, is much efficient and ideally smaller than what you would have for like something like Python. And plus, you know, Python in general is like an interpreted language also, the C Python runner which it has. So that's also like one of the core contributing factors. But if you intuitively try to understand, you would be able to understand that, okay, this makes some sense. Then of course, there is a concept of compiled languages and interpreted languages, which, you know, most of the people know in some way or another. Most of the people have talked about like compiled languages are fast, interpreted languages are generally slow, but then you have another class of languages which are just in time compiled, which is JavaScript and Java also as well. So these languages also exist and they are like pretty much close to C and C++ in general. And if you look at Bun, for example, Bun is also very impressive because it runs the fastest. It's similar to how fast Go is. So that's like a cool thing to notice, right? But in general, what this basically means is until and unless you're using anything above I would say probably PyPy, right? Even PyPy is also fine, like 1.5 seconds, sure. Like you're 3 times slow. With PHP, the real downfall begins, and Python is in the dustbin, right? For this specific thing in general. Now, of course, there are implementations of Python also, which makes it fast. But the general idea is guardrails in place, your language is having compilers that can optimize things ahead of time. If it's interpreted like Python, it will obviously be very slow because you are trying to make sense of every line of code as the code is running, right? So that's why these things get slow, PHP and Python and all. So yeah, that's pretty much it for this video. Hopefully you learned something new. If you did, make sure you leave a like and subscribe to the channel. I will see you in the next video very soon.